Alright, let's do another example with linear kinematics. So in this question, we have a car that accelerates uniformly from rest at the rate of 2.8 meters per second squared for 9.5 seconds. It then maintains a constant velocity for 0.75 minutes. Finally, the brakes are applied. The car slows down and it comes to rest in 25 seconds. And we are asked here to find in part A, the maximum velocity of the car, and in part B, the total displacement of the car. So, the first step with any problem like this is we want to visualize what's happening. And to do that, although the question doesn't explicitly ask, as we're going to draw, it's not going to be too neat, but we're going to draw kind of a rough velocity time graph. So here we have time in seconds on the x-axis, and velocity, that'll be meters per second on the y-axis. And looking at our question, we have a car that is accelerating from rest. So we know that when we are accelerating on the velocity time graph, we'll have a straight line. And then it keeps a constant velocity for 0.75 minutes. So we'll have a constant velocity. And then finally, the car slows down when the brakes are applied until rest. So until the velocity comes back down to zero. All right. And one thing that I want to do is just add a couple of time values here. So we know that initially the acceleration happens for 9.5 seconds. So I'm going to write 9.5 seconds from there, this point to this point. And then we also know that the constant velocity occurs for 0.75 minutes. 0.75 minutes times 60 seconds per minute. If we type that into our calculator, we will see that 0.75 minutes is equivalent to 45 seconds, and that's important just to keep our units consistent throughout the question. So once we have that converted, this period of time is 45 seconds long. And then finally, our last stretch of time is going to be 25 seconds that we are decelerating. So we're at 25 seconds. All right, so it doesn't have to be anything too pretty or too fancy, but we have sort of a understanding now of what's going on in this question. So let's start with question 1. We're asked to find the maximum velocity of the car. And looking at our graph, we know when is this maximum velocity going to occur? Well, it's along this whole line. Here, when we're going up the velocity axis, the highest point we see is this line, and it's the same speed throughout this entire line up here. So if we can find the value, the velocity right here, we will know what is the maximum velocity. So to do that, I want to just look at this just look at this region here. So this is the initial acceleration. At the end of this region, so after 9.5 seconds, you'll see that we have reached our maximum velocity. So I want to find, okay, during this 9.5 seconds where we're accelerating, what is this speed here? What is this v2? Right there. And to do that, I'm going to just be looking at our initial acceleration phase. So, as with all of our other linear kinematics problems, step number 1 is to organize variables. So, in the question, we are given an acceleration that is 2.8 meters per second squared. 2.8 meters per second squared. We are also given a time. Remember, we're just looking at this initial acceleration phase. So how long does that last? Well, it's 9.5 seconds. So time equals 9.5 seconds. And there's one more piece of information about this acceleration phase, and that is the speed that we begin at. You can see in the question it says the car accelerates from rest. So that tells us that v1 is equal to 0 meters per second. And then our unknown that we're trying to solve for, once again, is this final velocity. Here we call it v2. So we know v1, but we're looking to find what is v2. And that will be our maximum velocity. So we have our variables organized. Let's move on to step 2. Step 2 is to choose an equation. Choose an equation. So to do that, remember, go back to step 1 and look at our variables. So we have a, t, v1, and v2. And we will bring that over to our chart over here and say which of our equations here contain all the variables that we are looking for. So remember, we have v1, v2, acceleration, and time. So we will be looking at equation 3. Again, your teacher or your textbook might have different numbers, but what's important is to look at this equation itself and the variables that are used in it. So we're going to take this equation 3 and we're going to write, because we have a, t, v1, and v2, that tells us to use equation number 3. Okay, let's move on to the next step, which is step number 3, is to plug in our variables. Plug in the variables. So now that we chose equation 3, let's just quickly rewrite it to begin with. So the acceleration is equal to v2 minus v1 all over time. And now let's start plugging in these variables. So here's our 4 variables that we are going to plug into the equation. So first, the acceleration, 2.8 meters per second squared. Remember, that value was given to us here. Is equal to v2. Well, what's our value for v2? We don't know. So in our formula, we're just going to keep it as v2. Minus v1. Our value for v1 is 0 meters per second. So I'm just going to write a 0. And over time, time 9.5 meters per second. 'I'll do this in green, 9.5 seconds. And now let's just rewrite this equation, taking out the brackets and just clarifying what we have. I'm going to keep our V2 in green just so that it's clear, it's our unknown. Over 9.5 seconds. Okay, and that brings us to step 4, where we need to rearrange this equation to isolate for V2. Step 4 is rearrange to isolate the unknown. And I will just move things around a little bit just to make some more space. Let me just move this out of the way as well. Okay, so rearrange to isolate for the unknown. So with this equation, how can we isolate V2? Well, we're going to have to get rid of this 9.5 seconds, that's a division, and bring it to the other side of the equation. So since it is a division on this side, when we bring it to the other side, it's going to be a multiplication. So here we will be left with 9.5 seconds multiplied by our original 2.8 meters per second squared, equal to V2. So you can see our two equations, they're equivalent. The only difference is this 9.5 has been brought up to be multiplied by the 2.8 meters per second squared. And then it's just a matter of typing this into our calculator. I encourage you to try this along with me. I got an answer of 26.6, and the units on that, we can see meters, and then seconds squared, so the exponent 2 will get canceled out, and we'll be left with just meters per second, and that is what we are looking for with a speed. So going back to significant digits, in this question, all of our answers are given with 2 significant digits, or all of the variables, have 2 significant digits. So when we present our answer, we are going to just leave it at 2 significant digits. We can write a little statement to close this off. We're going to say, therefore the max velocity is 27 meters per second. And that is part A. Moving on to part B, the total displacement of the car. So what do we know about the displacement? We know that the displacement, delta D, is equal to the area under the curve of a velocity time graph. So remember from your lesson that the area under the velocity time curve is equal to the displacement. So I'll write that out here. The displacement is equal to the area under the curve of our VT graph. That's velocity time graph. So what I'm going to do here is copy this. I'm going to copy it and bring it down here. And just, I'm going to make this a little bigger so we can work with it a little bit easier. I want you to note that when it says area under the curve, this is the curve that it's talking about. So under the curve, it's referring to the distance between the curve and the x-axis. So in this case, it's what you see shaded in green. So the easiest way to solve this is going to be to split our area of this trapezoid into 3 easier areas to calculate. So we're going to have an A1 here. This I call A1. We're going to have an A2, and I'll try to color code these to make it more clear for those of you who are following along. If I can get this to get shaded, let me try this again. I want a nice box so that this is clear for all of you. Don't know why this is not working. I should be able to make a box here. Let me try one more time. There we go. So that is our A2. And we will have also an A3 with this triangle on the end. This will be our A3. So we have 3 areas that we will be able to calculate. And again, I want to say, write this as a note, that the area under the curve, which is equal to the displacement, and this is equal to A1 plus A2 plus, I forgot the 1, A1 plus A2 plus A3. And I'm going to keep these color coded so that it's easier for you guys to follow along. So our A1, A2, and A3, when we add them together, they will give us the total displacement. So let's start calculating these areas. So A1, we have a triangle. So the area of a triangle we know is 1/2 base times height. Now let's look. So this triangle, we have a base of 9.5 seconds, right? And the height, well, this height is actually the value that we calculated in the previous part. It's the maximum velocity. So this is actually, remember, our V2. This is the height of our triangle. So 26.6. I'll move this a little bit out of the way. This is actually 26.6 meters per second. So again, that was our maximum velocity that we calculated in the previous question, but it is also the height of this triangle. So when we plugging in this formula, we have 1/2. Remember, the base was 9.5 and the height 26.6. So 9.5 seconds times the height 26.6 meters per second. Calculating that, I encourage you to follow along here with your calculators. We have that A1 is equal to 126.35 meters. All right, let's move on to the second area. So A2. And what is A2? So A2 is a rectangle. So the area of a rectangle, as we know, is just base times height. And so the base of this rectangle is going to be 45 seconds. And the height, well, if we look at our triangle, it's going to be the same height. So the height of this A2 rectangle is also 26.6 meters per squared. So let's plug those values into our formula. So that's the base of 45 seconds and the height of 26.6 meters per second. Plugging that into our calculator, we get a final answer of A2 of 1,196 meters. And lastly, let's move on to A3. Do this in blue to keep it consistent. So again, it's a triangle. What is the area of a triangle? Well, it's 1/2 base times height. So again, we have to look at this triangle to find our dimensions. So our base is 25 seconds. And the height, well, it's the exact same as A1 and A2. It's the same height. So our height is also 26.6 meters per second. So the base, 25 seconds. And the height, 26.6 meters per second. So A3, putting this into our calculator, make sure you get the same answer as I do, 332.5 meters. All right, we are just about finished here. I'm going to bring us back up to the top. All that's left to do is add up these areas. So again, I will rewrite our equation for the displacement, and that is A1 plus A2 plus A3. And just keeping the colors consistent here. Okay, so let's add up these areas. A1, 126.35 meters. 126.35 meters. And A2, we had 1,197 meters. 1,197 meters. And finally, the value for A3 was 332.5 meters. 332.5 meters. Typing this into our calculator, we will get a final answer of 1,655.85 meters. And almost our final answer. Again, we have to look back at our question and see that we only use 2 significant digits in the given data. So our final answer should also be in 2 significant digits. So delta D is equal to, we're going to round this to 1,700 meters. But what we're also going to do is use scientific notation and bring this decimal back. So we're bringing it back 1, 2, 3 spots. So 1.7 times 10 to the 3. So this number 3 is the number of decimal spots. We're bringing it back. So 1, 2, 3. And we're rounding it to 1.7 times 10 to the 3 meters. And that is our final answer. We're going to write a little statement. So that means the total displacement is 1.7 times 10 to the 3 meters. And that is our final answer.